Hey students, logic students, this is your Professor O'Millianchuk, and today I'm going to be talking to you about semantics of assertion and just the different kinds of truth and falsity that are going to come up in this course. All right, so just by way of review, I'll go through this kind of quickly just because we already talked about this in the previous lecture and you can see the video. But we talked about models. And what those are formally is just ways the world could be. And what you have in a model is basically a description of the way the world could be. And if you satisfy the model, right, your atomic assertion then will be true, right? But if not, then the atomic assertion will be false. Right? How do we construct a model for our little language that we called CL star? That makes use of the kind of the object predicate distinction. Well, what we do is we specify a set of objects, specify which of those objects belong to each of the two predicates, and then specify which objects are labeled by each of the two names. So what you do is you come up with a domain, a predicate function, and a term function. It ends up kind of looking like this. All right, I know I'm going through this kind of quickly. Again, just see the previous lecture if you were a little lost, right? But what this tells us is that A is F, A is G, and B is G. Those are all true because what A and B are naming in each of these are in the extensions of the predicate. So A is in F, A is in G, and then of course B is in G, right? By contrast, B is in F is false because, well, Boston is not in the extension of F, all right? So that's just by way of review of what we talked about in the last video on models. Another thing we talked about too is just the semantics of CL that's fully specified. So if the referent is in the referent of the name is in the extension of the predicate, then the atomic formula is true. And then the compound formulas, the ones that we can make with arrows, those are false if and only if the antecedent's true and the consequent is false, otherwise it's true. And we introduced this little thing called a truth table today, or the other time we talked, and that is something you should be memorizing, right? That pattern, TF, TT, and then the four different possible ways P and Q could be, okay? We talked about logical truths, right? I think, no, wait, this is new material, I believe. This is a logical truth. Wait, no, we talked about this. Anyway, I'm getting a little mixed up, but here, here's the thing, right? PRLP is always true, okay? There's just no way that you can make it false. And what we mean by logical truth, this little adverb logically, that's gonna be like a necessary truth, right? And the adverb logically, what it does is it means basically every model in your language is one in which the formula is true, right? So a logical truth is one in which every model, the assertion is true, okay? Sometimes they're called necessary truths in other languages and other textbooks. And that's just synonymous with logical truth in this class. A necessary truth just must be true, no matter the way the world is, okay? Also, I just want to draw your attention to the little IFF in that previous sentence. That's not a typo, actually. That's the way logicians talk sometimes. I know it's kind of weird, but the IFF part of our definition is meant to indicate that the property of being logically true, this side, right, is something that is equivalent with being true in every model, okay? And so that means then that they stand and fall together. All right, and that's important. So if one is false, then the other is false. All right, or if it's true, then the other is true. Okay, those are equivalent ideas. All right. All right, so let me at least kind of get maybe for some of you visual learners, let's talk a little bit about why is it that this is a logical truth. Okay, let's explain this a little clearly. Okay, so here we have G of A being true, okay, and so then what we have there, this sentence is basically is that if A is in G, then A is in G, and of course that's true, but especially in the case where A is in G, right? It just so happens to be the case that A is in G, all right? But if you look at this model now where this is saying that this is right here. This part is saying A is in G, but the model says that's false because here's our model, right? A is not in G. But just think of it this way, right? If A is in G, so imagine A being in G here, then A is in G, and so it has to be true. Okay, so you have to kind of use your imagination a little bit here and think about this, right? The atomic pieces of the sentence are not going to determine necessarily the truth of it. So you think, oh, how can you have two falsehoods adding up to a truth? Well, use your imagination. Suppose that A was in G. Okay, well then A would be in G. Okay, that's just basically the idea. It's pretty simple, right? So let's talk about logical falsehood. Okay, that's just going to be the opposite of logical truth, right? An assertion is logically false in a language if and only if it is false in every model of the language, right? So no matter what model we use, no matter how the world could be, right, this statement's going to be false. Now, the problem with CL and CL star is that they're just too simple to express logical falsehoods. Okay, so you might try, and the only way I can really introduce to you so far with what we got is just what I kind of talked about last time. Remember, I was like, okay, let's suppose this PROP is false, right? So then our compound formula semantics then would say that the antecedent P is true and the consequent P is false, right? But that's a contradiction, right? And now contradictions are really good examples of logical falsehoods. Those just can't be true, right? It doesn't matter the way the world is, you can't have a contradiction coming out true, and it's just a formal thing, right? I mean, if you think about it, like the sun is shining today, and the sun is not shining today. Now, you could probably read that, in different ways. Well, at what time, right? Well, we can just say, well, the sun is shining all the time today, and it's shining. It's not shining all the time today. Okay, that's a contradiction, all right? Just think of that, associate that with logical falsehood. Logical falsity is false in every model. Okay? All right. Logical contingency, it just has to do with not being logically true and not being logically false. All right? So, basic idea is pretty simple. An assertion is logically contingent in a language if and only if it's true in at least one model for the language and false in another model. So here, these kinds of statements are really going to depend upon the way the world is. All right, so you can kind of separate those from, the other kinds, right? You have the never trues and the always trues, and then you have the ones in between that are sometimes true, right? The never trues and the always trues, those don't depend on the way the world is, okay? But the sometimes true, sometimes not, well, that's going to depend upon the way the world is. Okay, so logical contingency is important, and that's how you need to understand it. So the statement FA arrow GA is a logical contingency. And that's because you have, well, at least one model where it's true, the first row there, and at least one model where it's false, the second row. Now you have a wealth of riches here. You have a couple other rows where it's true, but you just need one true and one false to get contingency. Okay? Now, I want to say this, right? In 3 cases, it's true that if A is in F, then A is in G. All right, so I want, if you're, a lot of students get kind of confused about conditionals. They're just like, well, why is it that you can have a false antecedent and have a true conditional? And for those of you who have been wondering that, have been kind of worried about that, like that just doesn't seem right. This is going to be kind of my picture proof of that, right? I'm gonna draw some pictures. All right, so here's some Venn diagrams. Let's represent row 1 there. Okay, here's a model, right, that makes that row true. Okay, so both of the atomic sentences are true, right? A is in F, all right, and A is in G. Okay, so those two are true, and so obviously if A is in F, then A is in G. Okay, let's look at the third row. Here, A is not in F, but it is in G. Now, why do we think that's true? Well, look at where A is, and now think about just the statement that the arrow is representing. Okay, you have to think about three things here. You can't just think about this and this. You got to include what this is saying too. If A is in F, then A is in G, and that most certainly will be the case. Now, it just so happens that A is not in F, but if it were in F, then it would be in G. See what I'm saying? Okay? All right. Same story here, okay? If A is in F, then A is in G. This model right here makes that thing true, okay? However, look at the second one now. Right now we have to follow what the row is telling us. Okay, so A is in F, so we put A in an F there, but A is not in G. Okay, so now A is outside the boundaries of G, but it's in F. Now what happens to our statement? If A is in F, then A is in G. And we consult model row 2. Well, that comes out false, okay? That comes out false. This statement, if A is in F, then A is in G, becomes false on that particular model, right? So the way you kind of have to think about these sorts of conditionals is that they're kind of innocent until proven guilty, right? So this model can make it, this model right here shows that how these are kind of, veridically innocent. If you don't know what the word veridically means, it has having to do with truth, right? They don't commit any crimes against the truth, right? Whereas this one does, okay? Here you have some funny business going on. And so you wouldn't want to say this, otherwise you'd be saying something false. Maybe you'd be lying, right? Depending on what your intentions are. Okay. All right, so that's logical truth, logical contingency, and logical falsity. Now we come to the central concept of this class, which is logical entailment. And basically from here on out, we are going to be studying different methods of entailment. Right? So what is entailment specifically? Well, it's the idea that some assertions demand the truth of others. Okay, and the word demand here is not like a fist-pounding kind of demand, like, hey, you gotta be this way, but rather what you have is a kind of gravitational pull, you might think of it that way, is that some assertions, they're just gonna make it the case that others are true. All right, and so in this class we use the word entailment for that. In other classes, you'll hear the word implication. Logical implication is synonymous with entailment. Okay, that's what I want you to take away here. Right? Implications and entailments, those relations are just the same. So we've talked about modus ponens. If A is in F, then A is in G. Right? Premise 2, A is in F, and then the conclusion, therefore A is in G. Right? There is no way the world could be where the last assertion is false and the first assertions are true, the first two assertions. All right, so that's a really key point. So what we say here then, okay, given this argument form, is that the premises logically entail the conclusion. Okay, they demand that the third be true, and not only do they demand it be true, but they make it the case that it's true. If that makes sense. Now, there's going to be exceptions to that, all right? The reason, and we'll get into that, okay? But what we want to think about is that if these two are true, then this one's got to be true, okay? So if the first two are true, then the third's got to be true, okay? Now, it might turn out that you have some false premises, okay? And you can have a false conclusion, but the entailment relation will still hold, right? And we'll get into why, all right? I know that's kind of a strange idea. Anyway, just to get the kind of formal definition down, in your notes here, is that an assertion P logically entails an assertion Q in some language if and only if all models of L where P is true are those in which Q is true is as well. All right, so that's the idea. Wherever P is true, then Q is going to be true. All right, that is the idea. Entailment's going to hold. Now, if P is false, well, you just don't worry about those. Okay? What we want to know, what we're interested in, is the truth of P and whether those same models in which P is true are those in which Q is true as well. Logical entailment has a special piece of notation since it's so important, right? So when we say P entails Q, we denote it here by this little like double turnstile thing, the P double the turnstile Q. Now, when we use this notation, we can also denote what a logical truth looks like. Right? So what we would do then is we just kind of we'll say that the logical truth is Q. We'll leave off the P and we'll just write double turnstile Q. Now, what that means is that Q is true all by itself in every model. Closely related to logical entailment is logical equivalence. Right? Equivalent expressions always say the same thing. And they mean the exact same thing under the same conditions. So whatever conditions you have, your conditions are going to make both of the expressions true or both of them false. Okay, so here's the formal definition. Right? Two assertions P and Q are logically equivalent in a language if and only if P entails Q and Q entails P. So we're making use of entailment here. Entailment is something that we can use to analyze equivalence. But what that means basically is that every model where one of them is true is a model that makes both of them true. Okay? So we have a special piece of notation there. We have kind of this thicker looking double arrow, P double arrow Q, to indicate that P and Q are logically equivalent. Equivalence is a very powerful idea, right? Because what it does, what it allows us to do, is substitute one expression for another without a loss of meaning. Okay, so here's a sentence in CL, okay, and it's kind of complicated looking. You know, you have, so here's, if you're wondering, this is the main connective here. This whole thing is the antecedent, right? Now, what that is logically equivalent, as it turns out, is actually just Q, right? That's actually the case, and I'll show you why. Okay, let's go back. Let's use this thing called a truth table again. All right, if I were to work out this truth table, and I'm going to show you how to do this in later lectures. So if you're kind of lost here, if you don't really know what's going on, but if you figure out what the main connective is, and this column here, right here, it's representing that arrow right there. Just so you know, it's not representing that one. That's just the way it kind of centers up in the PowerPoint. So I just want you to be aware of that. But we're talking about that arrow there. That's what it's going to say in each of these rows: T, F, T, F. And as you'll notice, right, it says the exact same thing as Q does over here. You have T, F, T, F. Okay, and so since they say the same thing under the exact same conditions, they're logically equivalent. That is, they entail one another. All right, a couple theorems you should know about this stuff. A theorem is just kind of like it's like a big logically, they're logically true ideas, right? So all logical truths are logically equivalent. It's kind of a meta principle. All logical truths are logically equivalent. And if you take a moment to reflect on that, I think you'll see why, in the intellectual sense, why that's true. Because logical truths are true in every model, so it doesn't matter what the conditions are, they're always true, and so therefore they say the same thing no matter what. And so therefore they're logically equivalent. Since logical truths are true in every model, they are true under the exact same conditions. Oh, I just said that. Hello. All right. For any formal language L, then, if P and Q are logically true in L, then P and Q are equivalent in L. Right? The same goes for falsehoods. Okay. For any formal language L, if P and Q are logically false in L, then P and Q are logically equivalent in L. That's because logical falsehoods are false in every model. Right? They're false under the exact same conditions. We have a special piece of notation for logical falsehoods. They look like an upside down T, right? It's called bottom. That's what it's officially called. That's its name. Right, let's talk about logical consistency, right? What does consistency mean? Well, let's think of it this way, right? The members of a set of assertions could be true at the same time. Okay, so what you're looking here for is, you might have a collection of sentences, and when they're consistent with one another, that means there's one model in which all of them are true together. Okay, and to kind of illustrate this idea from the philosophy of religion, some of you might be interested in this. There's an argument that's sometimes given that's given against God's existence. So this is this is an argument of atheism, right? So you have like a premise like this that it says God is all good, right? So there's a sentence, and then sentence 2 says God is all powerful, right? He's able to prevent evil, and then you have the third premise that says God exists. Okay, and so actually, it's a kind of a mistake that I just made to call these things premises. What they are is just assertions, right? They're a set of an assertions. They're a triad of assertions, right? And so what we want to think about here is whether or not they're consistent. All right. So for our purposes in our class, a set of assertions P, Q, R, or however many you might have, right? They're going to be logically consistent. Or I think the textbook that you're reading now changed. It's called logical satisfiability. So that's the same thing, right? Logical satisfiability is the same thing as logical consistency. Okay. Those two things. That set is going to be satisfiable in the language if and only if there's at least one model in the language where every member of the set is true. Okay, otherwise it's logically inconsistent or unsatisfiable. All right, so look, if you're interested in philosophy of religion, right, lots of people debate this argument. It's called the logical problem of evil because basically the idea is that evil is taken to be just inconsistent with the existence of a God who is both all-powerful and all good. So look, you might have a deity left over, right, but it's just not all good. So that would be like Zeus or somebody like that, right? Or you'd have a God who's just not all powerful, right? He just can't stop the evil from happening in the world, right? And there are some theologians who go that route. Okay. Now, if you're interested in this from a maybe more, if you're interested in this from an orthodox perspective, right? You might check out the book by Alvin Plantinga called God, Freedom, and Evil. And what he's up to in that book, he's not trying to prove God's existence or do any kind of evangelism or anything like that, so don't worry about that, okay? He's a philosopher, though, and what he's doing in this book is he's basically kind of telling a story which ends up constituting a logical model, right? It's a kind of model that he gives in which all three of these can be made logically consistent, right? He's trying to develop what is called a logically satisfiable model. And this was written in the 1970s, and for the most part, there is wide agreement that Plantinga pulled it off, right? This argument doesn't it doesn't have as much traction as it once did in the 1950s. And so, there are responses to Plantinga, of course, that, dispute some of his key ideas. But there are, then other philosophers reply and say, well, there's ways of kind of fixing his ideas, right? And you end up getting consistency. And so it's a very interesting debate. It's been going on now for, almost 40 years. It's over 40 years now, and it's a great little book if you're interested in this and you're interested in logic and the relationship it has to other areas of philosophy. I really recommend it. Check it out. Okay, let's talk about truth functionality, right? And I'm going to use the abbreviation TF here in the slides, right? You can know the truth value of a compound assertion if you know the truth value of the components. Now, this isn't always the case, but it is the case in our language, all right? So here is the sentence, we might have been looking at. If Austin is funky, then Boston is funky. That's a truth functional statement. Okay, that's a truth functional statement. So if the consequent is true, then that whole statement is true. Okay, as weird as that might be, that is the case. All right, it's written in the indicative mood, given its grammar. It comes out true if it's the case that Boston is funky. It comes out true if Austin is not funky. All right, it's just saying if Austin is funky, then Boston is too. Right? It's actually kind of it doesn't actually claim that much, believe it or not. So you have to kind of think of it that way. All right, it's a truth functional statement. Here's one that's not truth functional. It's possible that there's an odd number of stars in the universe. Okay, so you can't break that down into any component parts and figure out whether or not that's going to be true. I mean, this is either true or it's not, right? And it certainly seems like it is. Okay, it's possible. Now, you might have to specify in what sense. Maybe it's in the epistemic sense. For all we know, right, there's an odd number of stars in the universe. Okay, maybe the Big Bang could have worked out a little bit differently, right? There would have been a slight variation and there would have been one more star. Okay, there's that kind of idea. But that's not a truth functional idea. That has to do with modalities and possibility and necessity and all those kinds of things. For our purposes, though, an assertion P is truth functional in L if and only if its truth in the language depends only on the truth of its atomic components. Okay, so the truth of the compound depends on its parts, all right? The truth of the whole depends on its parts. So is CL truth functional? You better believe it. Okay, is this thing a logical truth? It is, right? The way you kind of figure that out now is you just kind of look at the consequent and say, oh, that's a logical truth. And if the consequent is logically true, then the whole thing is a logical truth. Okay, this is the practice portion. And what I'll have you do is go through these. All right, you can work through these by yourselves. The lecture's about a half an hour long. And you can kind of figure this stuff out, right? And what we'll be doing then is working on homework that will get into this kind of stuff. All right, so the next lecture, I believe, is going to be about that. Just one moment here.